Okay, so welcome back. So today's lecture is a little different from the last two because it's kind of purpose is mostly remedial. That so we want to go over some basic facts about functions of several complex variables in order to set the stage for Hörmander's theorem in several variables, which hopefully we can start tomorrow. Okay, all right. So let us begin by recalling a few definitions. So as in the case of one variable, in several variables, holomorphic functions can be defined in many different ways, but there is a natural way for us. So we'll say that a function f in C1 omega, where omega is some open set in Cn, is holomorphic d bar f is equal to 0. So recall what d bar f is. D bar f is the sum df over dzj bar. dzj bar. I'm not using the summation convention, I'm writing the summation sign. So this is equal to 0, which is to say so therefore when you look at it, all it is saying is that it is holomorphic in each variable. So that's all there is to it. Okay? However, there is more to it because here we have made the completely redundant assumption that f is in C1 omega. As it happens always with holomorphicity, this kind of thing actually holds under much, much weaker hypothesis. All that we really need is that we have a function, just function, set theoretic function, which is holomorphic in each variable. So this is, we are not going to discuss this, this proof depends on some properties of subharmonic functions and stuff, but it's a truly remarkable thing that, as you know from calculus, if you don't, please revise, that if we have a function which is continuous, a function of several variables which is continuous in each variable, then the function itself need not be continuous, it's a function of several variables. So what this is saying is that if we make the hypothesis that a function of several complex variables is holomorphic in each variable, then it is automatically holomorphic, which in particular means it is continuous, analytic, and so on. So something really subtle is going on here. Okay, that's the first thing I wanted to recall. Okay. Then let us compare the properties of functions of one variable with those of several variables. So basically, three things can happen. So if you look at a property, three things can happen. The first thing is that several variables is not different in some respect from one variable. I'll give examples of each of these phenomena. The second one is that some adjustment is needed. So they're basically the same, but you have to think of it in the correct way. Some adjustment of point of view is needed. Adjustment. And finally, what can happen are new features in several variables. So examples of one are many. For example, we know in one variable holomorphic functions have power series. Similarly, in several variables, holomorphic functions also have power series. In one variable, these power series live on disks. In several variables, they live on polydisks, so and so on. So there are many facts about one variable which quite easily generalize to several variables. One of them, for example, so I'll just say examples of one. I mean, there are many more. For example, complex analyticity, which is to say existence of power series. Then the maximum principle. Recall what the maximum principle says. If you have a holomorphic function and its absolute value attains a local interior maximum on a connected domain, then that function is necessarily a constant. And basically the same thing works in several variables, and so on. Let's look at an example of two. Okay? Let's look at the identity principle. So the following version of the identity principle does hold in several variables, including one variable, of course. So let omega be a domain in Cn, and little omega subset of big omega an open set. Now you take a function f which is holomorphic on omega, whose restriction to this little open set, I will also say that omega is not the empty set, just to preempt any issues. Suppose that we have a function little f which is identically 0 on this open, then f is identically 0 on omega. Of course, this is well known to be true in one variable, but in one variable there is also a stronger version of this. I'm sure everybody remembers that. So what is that stronger version? So in one variable, so here I didn't say what n was, I should say n greater than or equal to 1. In C1, so suppose we have A subset of omega subset of C, okay? And this I need to take connected, of course. And A has a limit point in omega. So what that means is there's a point in omega if you take an arbitrary neighborhood that intersects the set A, right? So, and then if we take a function which is holomorphic on omega, such that f restricted to A is 0, then f is identically 0. This kind of statement will not be true in several variables. Can anybody offer an example? Yes, okay, so, okay, let's say, so what is omega now? Omega is the whole of C2, I think. Yes, and little f of Z1, Z2 is? Okay. Yes, and then? Yeah, zero set has lots of limit points, right?
But it doesn't contain zero set.
Yeah, so the zero set has lots of, okay, so what is A then? A is the whole zero set, right? But f is not identically 0. I don't see, there's no harm in putting the Z2, I could just take one of these, right? Right. So why is this happening? Let us like stop a few seconds to think why such a thing is happening. Okay? The fact is if you look at the zero sets of holomorphic functions, they are very different in one variable and several variables, as they must be, because they are of complex codimension 1. Okay? So in one variable, these are exactly subsets of the domain which have no interior limit points. So therefore, if you have a function which vanishes on a set which has an interior limit point, it has to be identically 0. However, as this example already shows, the zero sets of holomorphic functions of several variables, they are pretty large, okay, from that point of view. So therefore, in this type 2 case, you have to be just careful. You don't want to make mistakes, so you want to be just careful. Now we come to number 3, which is the interesting case. New phenomena. So let's look at a result which has absolutely no analog in one variable. So let us look at the following proposition. So let omega 1 be a domain in Cn, and now I will specify that n is greater than or equal to 2. and let K subset of omega 1 be a compact set such that if you look at the difference, omega, which is omega 1 minus K, so allow me to draw what is it, two-dimensional picture of some four-dimensional or higher situation. So you remove this part. Let f be a holomorphic function on omega. Then f extends holomorphically to omega 1. So there exists a function capital F in omega 1 such that little f is big F restricted to omega. Even before we start discussing why this thing might be the case, the first thing to note is that this is obviously false in one variable, right? Didn't I say that? Oh, I said that, but I didn't write that. Yes.
You said yesterday that for you domains are always connected.
Yeah, but I didn't say omega is a domain. So omega 1 is a domain. That's what I said. So I think here's the point. So I'll just say here, okay?
Connected domains, there is some.
Okay. Connected. Thank you. Yeah. Okay. This is false in one variable, right? Why is this false? 1 by z, right? So 1 by z, 1 over z minus p, where p is some point here. That already provides a counterexample. So we have to understand a little bit where this is coming from. What are the features of the number 2 and higher numbers that the number 1 doesn't possess, and as a result of which this thing happens? So there are several ways of looking at it, but since we are mostly talking about the Cauchy-Riemann equations, let us try to approach this question from there. Okay? So let us see. So in one variable, so the Cauchy-Riemann equations is just actually one equation, or two if you take the real and imaginary parts. It's one complex equation or two real equations. So the one complex equation is written as du over d z bar equal to g, and no restriction on g. What about more variables? It's easy to write down the inhomogeneous version of the equations. So let's look for the equation for functions. So we are looking at du over d z1 bar is some function g1, du over d z2 bar is some function g2, dot dot dot, du over d zn bar is some function gn, okay, on omega. And immediately we see that there is a fundamental difference in that I cannot specify this g1 through gn independently. So there's a compatibility condition that must be satisfied, because after all derivatives commute. Okay? So therefore, if we look at, for example, d gj over dzk bar, that is the same as d square u dzj bar dzk bar, if there is a solution, of course. But then this I can switch the order of differentiation, and this turns out to be the same as dgk over dzj bar. Okay? So therefore we must have, if there is a solution, we must have so first of all, in coordinates, dzj over dzk bar is dgk over dzj bar for all jk, or in terms of the notation for differential form, d bar g equal to 0. And same thing will happen if you look at the similar equation in higher dimensions, in higher degrees, excuse me. So if we have an equation d bar u equal to g, where G is a PQ form, then observe that d bar of d bar u is 0, which means immediately, assuming that this thing has a solution, which immediately means that we must have d bar g equal to 0 if we have any hope of a solution at all. This is of course the same thing as this done in a fancy notation. Okay? So therefore, we have an overdetermined system. So there are more equations than are necessary to determine the function u. So therefore, and that causes several new things, including this one. So let me try to explain how that happens. So before we begin discussing the proof of that result there, it's usually ascribed to Hartogs, but I think proved by Aaron Price or somebody. Yeah. So let us recall the situation in one variable with compact support. So solving with the compact data, so solving d bar with compact data in one variable. We already did this actually yesterday in the problem session, but let's quickly recall this. So suppose now we have a G which is infinity with compact support of C and want to solve du over dz bar equal to G. Okay? And we know what the solution is. The solution is given by the formula u of z is equal to, so please don't hang me if I get some of the signs or other things wrong. So this is given by g of, so I should say, I have to introduce another variable w, z minus w dvw. This is what we learned from draw yesterday. Let me comment a little bit about the meaning of this formula. Okay. Yeah. So this is all I really need, but it's good to understand, and I think Draw also said a few things. Okay. So this thing over here is a linear constant coefficient linear partial differential equation. I already said linear somewhere, right? Partial differential equation. So it is a theorem that for such equations there exists what is known as a fundamental solution. So what does fundamental solution mean? Or I should say, for that operator there exists a fundamental solution. So that means there exists a solution of du over dz bar is the delta function at 0, where of course as soon as you make the right hand side a distribution, you want the solution to be distribution as well, where this u is some distribution called the fundamental solution. I should probably use a separate letter. U is let's call it E. Okay. C in this case. Okay. So then if G has compact support, so then the solution of, so if you look at the convolution, E convolved with G, and you apply the operator to this, one can check that this is the same as G. So therefore, you can solve with compactly supported data by convolving with the fundamental solution. So what is this fundamental solution here? Actually, it is quite easy to find. So let us begin from the fact that the fundamental solution of the Laplacian in two variables. So now by Laplacian I mean Laplacian as meant by Laplace himself. So this is 1 over 2 pi log absolute value z. This can be, of course, proved in several different ways. There are also physical arguments starting from Coulomb's law or something that shows that. But this we know how to represent in terms of the z-bar operator. This is a d-bar operator. This is 4 times d square d, I shall have to write it in this order, dz bar dz. Okay? So I can read this equation as d over dz bar of so I'll pull the 4 inside, so that will become 2 and the 2 will become a power here, d over dz of 1 over pi, I can even pull the 1 over pi out, so 1 over pi log d over dz log z bar. Okay? And I leave it to you to differentiate this and see that you get exactly 1 over z. So therefore, from some basic electrostatics, you conclude that this formula is correct. Yes?
That formula, there is no.
Oh, there is no unique. This is our fundamental solution. Yes. Yeah. There are fundamental solutions. This is a fundamental solution. So in the case of the Laplace equation, this can of course be singled out by symmetry. But of course, for the Cauchy-Riemann, I don't have any such thing. Yeah. That's right. Yeah. Okay. Okay. So I think I should make another comment. Therefore, any other fundamental solution. Any fundamental solution, any fundamental solution of d over dz bar is of the form 1 over pi z plus h, where this h is entire. That's how it looks like. Okay, so I have this formula now, and let me try to use this formula in trying to solve the compactly supported problem in several variables. So now, want to solve d bar u equal to g, and this g is C infinity with compact support in Cn, n greater than or equal to 2, and d bar g is equal to 0. D bar, thank you. Yes. Okay. Well, there's an obvious thing to do. Since I don't really know how to do it in several variables, I'll just do it in one variable. So let's do that. So, let's, for simplicity, let's just take n equal to 2. So I have just two equations. I have the equation du over d z1 bar is g1, and another equation du over d z2 bar is g2. Okay? Nothing is lost by considering only two variables. Okay? Then I try the function v of z1, z2, okay, which is obtained by convolving only in the first variable with g1, the fundamentals, the special fundamental solution that we chose there. So therefore, this v guy is given as 1 over pi integral over c g1 of w z2 divided by z minus z1 minus w dv. So from what we saw there, of course this v, right hand side, everything is very nice, compactly supported and so on. So v is smooth and everything works. But what we also know, so let us see what we know about this. dv over d z1 bar is already g. I don't know about the second equation, but I have certainly solved the first equation. g1, thank you. Okay. Also, and this is important, so G has compact support. So let us say that the support of G is contained inside some polydisk. So support of G is contained inside this polydisk of radius a. So I have to put this data here. So G1, G2 are identically 0 if mod Zj is bigger than A. Okay? Such a thing definitely exists because we are talking about compactly supported things. Okay, now what we want to do is we want to say that if mod Z2 is bigger than A, then this guy V of Z1, Z2 is 0. Right? That's obvious. Is that clear? Okay. Which one? This last statement? Why this is the case? By the definition of V, if you make Z2 bigger than A, this numerator, the integral is 0, you're integrating 0, so therefore you're getting 0, right? Yeah. Okay, so let us save the new phenomenon and move here. Let's look more closely at this function V. So I know already that the derivative of V with respect to Z1 bar is exactly what I want. So I want to check what happens if I differentiate V with respect to the other derivative, other function, other variable. So let's look at dV over dZ2 bar. Okay, that is therefore d over dZ2 bar integral over C of G W Z2 divided by Z1 minus W dVW. Let me just make sure. Oh, there's a pi. Yes, thank you. Okay. All right. Now everything is smooth, compactly supported. I have absolutely no problem in pulling the differentiation inside. So this is therefore integral 1 over pi C. So d over dZ2 bar GWZ2 over Z1 minus W dVW. But what do I know about this? I think this is the punchline. So this guy over here is 1 over pi integral over C d over dZ1 bar G of, yeah, this is something we have inherited from Leibniz.
You have the subscript. Top ones are
G1s. G1s, thank you. Yes, yes. The top one is G1. And this one here is G2. Right? D, that is, yeah. That is some bad notation that we have inherited from our ancestors, but yes. But what is that? That, yes, that is just G2 because that we are convolving with the fundamental solution again. So this is just G2 over here. So in fact, thanks to the compatibility condition, we have been actually able to solve this equation. So I have a solution V. So we have therefore the following situation. So we have found a solution V. So found V such that d bar V is equal to G. So that is good news. And V has certain other properties. The second property is V of Z1, Z2 is 0 if mod Z2 is bigger than this number A, which is the size of a polydisk inside which G lives. And we have another thing, V is holomorphic on Cn, or C2 in this case I suppose, minus the support of G. Because there the derivative vanishes, the Z bar derivative vanishes. But what does this tell me? So by the identity principle, V is identically 0 on the collected component of C2 minus the support of G, where which contains the set mod Z2 is bigger than A, which is to say in the unbounded component, which means immediately that V is compactly supported. So in the problem session, I will ask you to find those V in those data in one variable for which the compactly supported data for which the solution is still compactly supported. But yeah. So what has this to do with the new phenomenon? So let's come back here. Proof. So it's the same thing, you just reduce it to the solution of a Debraj problem. So let chi be a function of the following sort. So chi is identically 0 on a neighborhood of k, neighborhood u of k, something like this. Or let's say it's just on k actually. On k, and chi is identically 1 on omega 1 minus u, where u is a neighborhood of k. So and now, of course, you look at the data G, which is given by d bar chi times f on omega and 0 on k. So this is, it's obvious that this G is one form with compact supports. I think the notation G is a C infinity 1 form, 0 1 form on, you can extend it to all of C in fact. Okay, so on K and 0 on Cn minus omega. Huh? Cn, yeah. As compact support. And then you solve, so there exists U, which is also of compact support, a function of compact support. Such that d bar u equal to g, and you take your function f to be the obvious thing, which is f minus u. Okay. Is it clear? Chi f minus u, thank you. After cutting it off. Yes. Chi f means extended by 0 into k, as usual. Cut off. Okay. So the point I wanted to make is that these new phenomena are appearing because of the compatibility situation. All right, so therefore we can ask a new question which is basically meaningless in one variable, and which is the following. So let omega be a domain in Cn, and let P be a boundary point of omega. Okay? Does there exist a function fp which is holomorphic on omega, and I'll just state it vaguely now, and singular at P. So does there exist a function which is badly behaved at P? What do I mean by this? That is, Fp cannot be extended to a neighborhood of P. Actually, this is also not quite right if you want to have arbitrary boundaries, but assume for simplicity omega has smooth boundaries, then this is a correct way of putting it. Okay. So for n equal to 1, the answer is no. How did I frame it? Yes, the answer is yes in this case, yes. Yes, you take Fp of z to be 1 over P minus z, for example, right? That will serve the purpose. And greater than or equal to 2, the answer depends on the point P. On omega and P, right? As we just saw there. So for example, if I take my domain omega, which was obtained by punching out k out of omega 1, at these points the answer is no, because every holomorphic function on omega extends not only to a neighborhood of this point, but completely through k. Okay, so therefore, it is important to figure out, so this is sort of a version of that so-called Levy problem. So it therefore becomes extremely important to characterize when the Levy problem can be solved, okay, in higher dimensions. So I will now just state a result and then explain a few terms in it. Okay. So this is one thing that I did write down today, because I didn't want to. Yeah. So important fact. So let omega be a domain in Cn, and the following are equivalent. Number one, for all P in B omega, there exists F P in which is holomorphic on omega, singular at P, in the sense described there. Okay, now omega of holomorphy which means that there exists a function f holomorphic on omega and singular at each point P on the boundary. So I'm sure in one variable you are familiar with functions with natural boundary on the disk and stuff. So this is the high dimensional analog of that. And number 3 is perhaps the most important equivalent condition. Omega is pseudo-convex. I didn't invent this really ugly term, but we have to just live with this. So omega is pseudo-convex, which means that there exists a strictly PSH, I don't want any strictly, I didn't invent this one also, plurisubharmonic function on omega such that the sets, so I have to give this name, strictly plurisubharmonic function phi on omega, such that the sets phi less than c are relatively compact in omega for all C in R. So what that basically means, what this jargon means, first of all, I will come back to what subharmonic is in a few seconds. But what this means is that we have a function which blows off to infinity as you approach the boundary. And what does subharmonic mean? Subharmonic means the restriction to each complex line is subharmonic. Morally speaking, subharmonic means the Laplacian is positive, and morally speaking, subharmonic means that the Hessian matrix, the complex Hessian matrix. So, okay, this means if you look at the matrix d square phi dzj dzk bar, this would be an n by n matrix. This is positive semi-definite.
Connection that I can bring also want PD bar.
Yes, this is just a coordinate expression of the curvature form dd bar phi. Very good. Okay, so how many I have got? 3 here. Okay, number 4, either omega is the whole of Cn or the function p of z given as minus distance minus log, log distance from z to the boundary of omega is ESH. So this one is sort of the way it is stated is kind of strange because we are asserting the existence of some function. Here I'm saying a concrete function is actually subharmonic. Okay. Yeah, if omega is bounded, this is an exhaustion function. Yes. Okay. But not necessarily strictly subharmonic. Yeah. If omega is bounded, phi is ESH exhaustion. And the number 5 finally brings us back to the Debraj problem. So for all q greater than or equal to 1, if G is a smooth PQ form on omega such that d bar G is 0, then there exists U which is a smooth PQ minus 1 form on omega such that d bar U equal to G. So the Debraj problem can be solved in arbitrary degree for arbitrary data. Okay, so that sort of summarizes what one would cover in course on SCV for a semester. But I have to tell you more because this notion of pseudo-convexity has to be made more precise and more tangible. So let us see how pseudo-convexity looks like. What does it mean? So pseudo-convexity. So this fact or result shows already that pseudo-convexity is precisely the condition under which I hope to be able to solve the Debraj problem. So we need to understand it better. So some examples. For example, every convex domain is automatically pseudo-convex. If the boundary is locally convexifiable, and I'll explain what that means. Then it is pseudo-convex. So what that means is that I can apply a local biholomorphic change of coordinates at each boundary point to make the boundary actually convex. So those are those domains are pseudo-convex, and so if now omega 1, omega 2 are pseudo-convex, I'll write it like this. Then the product is pseudo-convex, obviously. Not obviously, but one has to construct the plus subharmonic exhaustion starting from the two of them. And if omega j is an increasing family of pseudo-convex domains, then you can take their union, for example. I think I will, this gives us some idea how these things are, but we'll have another way of looking at this thing now, in terms of the geometry of the boundary. So maybe I will call that Act 1. Huh? Yes, that is right. So where do I put that? So 5. Yeah. Okay. Intersections are also pseudo-convex. So in one variable, every domain is pseudo-convex. Okay? Just as if you look at the real line, every open set is convex, right? There's nothing more to be said, right? In several variables, so that is why in one complex variable this condition plays absolutely no part at all. However, now the question arises how to identify pseudo-convex domains in an effective way. So here I have fact 2. Fact 2. So in order to state fact 2, let us recall the notion of defining function of a domain. So what is the defining function of a domain? So that means we have a smoothly bounded domain omega. And rho is a function. For simplicity, I'll assume rho is actually smooth on the whole of Cn, such that the domain itself is the set of points where this function is negative. Excuse me. And to guarantee the smoothness, the d rho is never 0 on the boundary of the domain. So that's a defining function, and it's not difficult to see that without loss of generality, we may assume that the length of d rho is actually 1 on the boundary. Okay? This is absolutely okay. So then I define the following object. So first of all, at every point P of the boundary, I denote by, so I have of course a tangent space. I have a tangent space TP of the boundary. So first of all, TP B omega is the tangent space. Tangent is to B omega at P, which is of course naturally embedded in the tangent space of the ambient space Cn, and therefore can be canonically identified with Cn. So this is exactly Cn, and by the isomorphism that Drawn has been using all along, I can isomorphically identify it with the T10 space. Okay. All right. So the complex tangent space, so the I'll just write HP of Bm. This consists of all those tangent vectors T in Tp B omega, which satisfy the following, and I will explain its meaning in a few seconds. D rho over dzj Tj equal to 0. So what does this mean? So this guy over here, so we are sitting inside Cn. This guy over here is a 2n minus 1 real dimensional real vector space. And it is not difficult to see that inside this real vector space, we can find an n minus 1 dimensional complex vector space. So what this is saying, this is the green space. And now I'm ready to define this object, which is going to play a very important role tomorrow and day after tomorrow. The Levy form of B omega at P is the quadratic form or the Hermitian form given by LP of T is sum d square rho over d zj z d zk bar tj tk bar, where T is in HP of B omega. So therefore, if you are familiar with the second fundamental form of a hypersurface, this can be thought of as the Hermitian part of the second fundamental form. And this is defined only, so this is defined only on the green complex subspace. So I think I have run out of space here, so I'll have to go to the other side to complete the definition that is needed for fact 2. Maybe I'll state fact 2 right away. So the following are equivalent. Okay, so let omega be a smooth bounded domain in Cn. Then the following are equivalent. 1, omega is pseudo-convex. And number 2, for all points P on the boundary of omega, LP is a positive semi-definite form on HP of B omega. Okay. So the advantage of this condition is that it can be checked effectively, right? So you write down the defining function, compute this matrix, compute this subspace, plug in all, so, and then there are ways of determining when matrices are positive semi-definite. Okay. All right. So I think I think I'll just state one more fact, and after that we can end. So I'll say that it is fact 3, and fact 3 will also need a definition. Okay, first we make the definition. Let omega be a smoothly bounded domain in Cn. We say omega is strongly pseudo-convex. Strongly pseudo-convex. If for each point P on the boundary of omega, LP is strictly positive definite, on HP omega. Okay. Is that? Obviously, a strongly pseudo-convex domain is pseudo-convex. There is no doubt about that. And there is a remarkable fact about them, which is worth noting, which we'll actually never use, but so fact 3 actually is so maybe I will just draw a picture in order to state fact 3 instead of stating it like that. So suppose this here is my favorite strongly pseudo-convex domain. Then at each point of the boundary, there exists a local change of coordinates, biholomorphic change of coordinates, such that after you do that, so you are going to get something like this. So this is the domain itself. So this part along this is strictly convex. So strongly pseudo-convex domains have a very easily understood boundary geometry. So what it is saying is that you can change coordinates at each point so that it is actually a strictly convex smooth domain. So unfortunately, there is no such simple description of the geometry of the boundary of a general smoothly bounded pseudo-convex domain. In particular, they need not be convexifiable. However, this will not be a problem because essentially the only fact about smoothly bounded pseudo-convex domains that we will be using is the fact 2, which is that this is a positive semi-definite form on this complex tangent spaces. All right, so I think this is what we basically need, and we'll stop here. Thank you. Huh? Oh, thank you.